The software we test is becoming more and more complex and more distributed recently. And we as testers and developers need to come up with new solutions and methods in order to keep up with the testing needs of such complex and distributed systems. And we have to do it safely in order not to harm the reliability and stability of our testing platforms and infrastructure. In the next half an hour, we'll present different challenges of implementing and scaling up our testing platform while maintaining it highly stable and reliable. And we'll present different solutions for basically solving these challenges. About myself, I'm a senior automation engineer at LivePerson. LivePerson is a leading provider of live chat and messaging solutions for small businesses and enterprises. If you have been lately in a live chat with a customer representative online, there's a good chance that it went through our service. A little bit about our scale. We have 3 billion visits per month, 200 billion API calls per month. Our service is deployed over 7 data centers all around the world, and we have about 6,000 virtual servers where our service is deployed and running. And due to the geo-distributed nature of our service, we had to establish a testing platform which will allow us to verify the functionality of our service from different locations around the world. So for this purpose, we have established a distributed testing platform which is mainly based on 25 scenarios, mainly end-to-end and high-level test flows. We have 300, and also the scenarios are mainly based on UI and web and mobile, written in Selenium WebDriver API and Appium for mobile. We have 350 executions of these tests per day. Our test automation code base is actually also deployed to the same data centers where our service is actually located also. And we have 70 virtual machines in these production data centers, which are actually dedicated to the execution of these tests. As you can see from the diagram below, we have tests running, for example, from our Sydney data center to our disaster recovery data center in California. We have other tests running from the virtual machines in our London data center into Virginia. We have other tests running from Melbourne to Melbourne itself, and so on. And we're all aware of the issue that we have when we want to scale up and increase the capacity of our testing while keeping up our system highly reliable and stable. And in most cases, we will give up on the stability and reliability of our testing platform for the sake of having more testing capacity and executions per day or per an hour or any defined amount of time. And by implementing a set of tools and methods and principles in our testing platform, we have achieved both scaling and keeping our testing platform as stable as possible. we have noticed that once our scale of tests went more and more up, we had more deployment of our test automation code base into the data centers where our tests are actually executed. It's because we had many more tests to run in these data centers and more modification to existing tests and new features which we wanted to add new tests to verify them in our product. And we had to define a process which will allow us to minimize the risk when modifying and deploying our test code base into the production data centers without harming the stability of our tests. So we said, why not apply the same software deployment principles that we apply into our software code, and also apply it into our test automation code base, which we deploy the same into the same data centers which our service run. For this purpose, we have established a multi-tier phased deployment, which is based on 3 environments. All these environments are located in our production data centers. The pre-staging environment is basically the playground where any automated tester can actually commit new changes into our test automation code base and test that and verify that his new functionality is working. Once the tests in the pre-staging environment are stable enough, they will be rolled out into our staging environment, and then they will be rolled out into production. And the difference between production and staging environment is only logical separation of how they reflect the status of our service. Because staging and production are basically the same infrastructure and the same resources that we allocate for each one, but my single source of truth about my service health is actually reflected in the production environment. And we have set a rollout criteria for moving our new releases of test automation code base into the next environment. We have set the rollout criteria as a failure rate that is less than, for example, 3% for a predefined amount of time. If my tests keep being stable for a highest amount of time and my failure rate is small, I can basically roll out my release, my jar or my RPM into the next environment and basically minimize the risk of inserting unstable code into my test code base. And we have also implemented another feature, another idea of feature flags, such way that if I add new functionality into our test, I will usually wrap it inside a feature toggle, which will allow me to disable this new functionality in my test if the deployment I needed to deploy this new test fast and I didn't have enough time to test it on the pre-staging and the staging environment. And this way I can disable an unstable functionality in my test by injecting a system property into the environment and basically turn off this new functionality. We also faced another issue, which is a major pain when you want to scale up your tests, and it's single point of failures. Once you start scaling up your test, you will notice that you will the failures for the access for the external access point you invoke in your test become much more sensitive to failures, because you have a high volume of tests, and each failure to this external access points will cause many test failures. And the rule of thumb here is that external access point and APIs will always fail. And I mean by access point and APIs is the services that is the external services that we invoke into our test in order to build up our test, not the services that we want to test, but the services that we build up the test upon them. So our test code should be tolerant to these external failures, and we have to provide the fallbacks to every access point that we invoke into our tests. To make the things more clear, we will take an example, the Selenium grid, which is a great tool for distributing our test sessions across multiple browser types and platforms. But the main issue with Selenium grid that is it can be a single point of failure to our test, which means that if my grid hub is actually down, all my tests will fail. And if I implement a failover mechanism which is based on a secondary hub or entire grid, which can operate on a standby mode, I can basically route all my get remote WebDriver requests into the secondary grid in case my primary grid is down. We can also, when we increase when our basic platform start to scale up more and more, our grid will also start to get bigger and bigger. And a tip I would like to give is actually break down the large grid that you have into smaller grid setups. And this way, you will actually have a redundant setup and highly available grid setup, which you can apply a load balancer into this small grids, and actually route your get remote WebDriver requests into the load balancer, and the load balancer will be able to distribute your test sessions across these grids based on the capability that this grid can give you. And we actually don't have to set up a load balancer on using a cloud provider or any complex stuff. We can actually implement a client-side load balancer into our test code by using open source software. For example, we have a client-side load balancer provided by Netflix called Ribbon, which can be easily integrated into your test code and will actually allow you to implement a load balancing service very easily, and you have to customize it a little bit in order to filter the grid routing based on the capability that each grid can provide you. And also, we can add more protection layer into our setup by falling back to other Selenium setup, which is not located into our network. For example, if I fail to get a new remote WebDriver session from my load balancer service, I can basically invoke the get fallback action And for example, take a new session from a cloud provider, such as source lab or test object.
Can I ask a quick question?
Yes.
Back to the previous slide. So you're saying you've got multiple grids. What about the nodes behind it? So if you're a company that has 10 nodes sitting on one particular grid, would you have to have 10 nodes for each?
Okay, let's keep the question for the for the end, and I will answer. Okay, another pattern that we can apply into our tests is basically circuit breakers. Circuit breaker mean that if repetitive requests to an external endpoint you have in your test are keep on failing, you don't have anymore to invoke again and again this external endpoint until it's healthy. In this way, you prevent unnecessary time-mod requests into the external endpoint, and you also minimize the load on this external access point. Circuit breaker basically have 3 states, which it can be in. If the requests are always successful, the circuit breaker will stay in its closed mode. And once we will start receiving more and more failure requests into our external endpoint, my circuit breaker will turn into open state mode, and it will directly route all the requests into my fallback without even invoking my primary endpoint. But while we are routing all the requests into the fallback, I want to check also that my primary endpoint might be back online again. So the open state mode in the circuit breaker will actually open will actually try to reach the external endpoint again and see if it's successful, and will actually close a circuit breaker again if the request was successful, or open it if it failed again. And there are many open source libraries which we can use into our tests in order to safely wrap these external endpoints, so we don't have any failures in our tests, and provide fallbacks for them, and also apply the circuit breaker. For example, we have histories also by Netflix, and another Java library called Failsafe, which you can find links to the libraries in the slides. Here's, for example, a histories command, which so instead of basically just calling our grid and ask it for a new remote web private session, we wrap haste invocation inside the histories command. So and basically we get all the safe functionality that histories provide you by just implementing the command invocation inside its API. And you also can provide it a fallback. So once the circuit breaker will be open, all the requests to new remote web private sessions will actually be routed directly to the fallback. And the second grid can be, as we said, the other grid which you have on a different network, or a cloud provider which you can fall back to if your network or system have any issues with the grid. Okay. I would like to study with you a recent challenge that we had in our company, where we wanted to increase the testing capacity we have for our Selenium test, and basically establish an infrastructure for Selenium where we can actually spin up multiple browser sessions on different locations worldwide in order to keep up with the testing capacity that we had to execute. And this is actually the setup we have came up with at the end. As you see, every cloud here is basically a different data center where our browser sessions are launched, and inside each cloud we have a cluster of virtual machines where we can launch these browser sessions. We'll do now a reverse engineering of the solution and see how we basically implemented this infrastructure. Okay, so we were given basically a cluster of VMs, and we were asked to establish upon it a Selenium infrastructure for spinning up multiple browser sessions of different types while keeping the infrastructure as stable as possible. So if I want to get a new browser session, I can get it without any failures that might happen during the launch and the spin up of the browser. And the primary question we had is how we can know how much browser sessions each VM can hold at the same time. We had many browser types at different versions, so we cannot definitely know how much browser each VM can hold inside this cluster. And there's another problem. What if my browser session hangs inside one of the VMs, or the Java memory heap increases and it affects other browser sessions inside my VM. So we had two problems. One, we wanted to do a proper allocation of the browser session inside the cluster. And second, that we want to keep our environment clean in order to have a very stable infrastructure for the Selenium tests. So basically, we thought, why not launch every session of Selenium browser inside an isolated unit, inside a container. So if we launch this Selenium container, which can start at the beginning of the test and basically terminate itself at the end of the test, this way I can keep my infrastructure very clean and stable, and I can know how much memory and CPU I can allocate for each container, and based on that I can basically define how much each VM can hold, how many browser sessions each VM can hold. And then my test will actually request to deploy a new Selenium container on the cluster, and the cluster will choose any VM to launch this container, and the test will actually connect with the container which was launched on one of the VMs. But we had another problem. We wanted to launch multiple browsers over the VMs in the cluster, and we wanted some kind of manager or orchestrator which can basically distribute and allocate all these containers over my one large cluster. So we thought, why not add a cluster manager inside our cluster of VMs, and this way the cluster manager software will basically know where to allocate a new container on which VM based on its free resources. And this way we can efficiently distribute a browser sessions across the cluster. And there are many open source cluster managers software which we can use, such as Kubernetes, Apache Mesos, Docker Swarm, which we can integrate and set up into our cluster and basically enjoy all the benefits that it gives us. So now the scale of my Selenium infrastructure is only based on the cluster capacity, and I don't have to deal with the distribution of the browser sessions anymore. And basically, I can initialize my remote web driver session based on the. I can basically let my tests communicate with the cluster manager, and the cluster manager in turn will launch my desired container inside the virtual machines inside the cluster, and it will return an external endpoint, and upon that, I can basically initialize my new remote web driver sessions. We have only one problem left. How can I let my tests communicate with the cluster manager? I need some sort of communication method or API, so I can basically ask the cluster for a new session and get it back into my test, so I can initialize the remote web driver. For this purpose, we have implemented an open source library for creating short-lived testing endpoints over container clusters called ephemerals. Ephemerals short-lived. The library can be highly integrated into JUnit currently, so you can programmatically launch your test environment from your test. It has also support for different cluster management system, so you can plug your own cluster management system, implement its API, and you are good to go. And this way, the scaling of your test infrastructure in terms of endpoints is actually only based on the capacity you have in your cluster. And also the APIs support any cloud platform that might have one of the cluster management systems that the API also support. This is the use case we have implemented finally by using Google Cloud Platform, Kubernetes, and Docker. And we did the container orchestration using Google Container Engine, and it's built in Kubernetes Cluster Manager in such way that if I want now a new browser session, I can call the ephemerals API, ask it for a new deployment task of a new browser, and it will communicate with the Kubernetes cluster manager inside my cluster of VMs, and Kubernetes will actually spin up for me a new Docker container, and it will return the external endpoint which was exposed by the cluster, and basically I can initialize my new remote web driver based on this external endpoint. And I can also enjoy all the benefits that Kubernetes give me in terms of safe deployments of these containers. So I can both keep my testing infrastructure scalable and also very safe to deploy to the cluster. Here you can see an example of a joint integration of the API. Here I basically initialize the Selenium ephemeral instance using the deployment context, which includes all the connection information about my cluster and all the authentication stuff I need to provide in order to connect into my cluster. And I provided what desired capabilities of the container I want to launch. And inside the test, at the beginning of the test, I can invoke the Selenium resource get methods, and it will start deploying the new container into the cluster. And in a few seconds, I will have a new remote web driver instance, which I can work with during my tests. Do you have time for a demo, a little demo?
No, I think we're running out.
No?
How long?
1 minute and a half.
Show something.
Yes, we have.
Before.
Okay, I'll show a little demo. Okay, here we define, I defined a test where I want to actually deploy now 10 browser sessions at the same time into my cloud. Zoom. It's a video, I don't know. Okay. So. Okay. Okay, you can find the open source library on GitHub. You can fork it, read the README there, and start to basically scale up your infrastructure based on cloud solutions and based on containers. So you can scale up while keeping your system very stable and reliable. Thank you.
Yeah.